Hi, folks. This is going to be a quick run-through of a Jupyter notebook that I have assembled that's focused on applying vector search, neural search, AI search, whatever nomenclature you want to use, to security logs. So you should be able to see my screen. We're going to walk through this. There's three examples. I'm using some proxy logs that have been fabricated with some tooling. Yeah, I think they're reasonably accurate to work with as test data. I have 1,000 log entries that show benign behavior, 1,000 log entries that show malicious examples of malicious behavior, and then 1,000 where that are mixed. There should be 950 that are benign and 50 that are malicious. So 950, 50, good, good and bad, right? So that's the data that I'll actually be working with in this. There's three things I want to focus on in this example. One is applying AI-driven vector search to exploit matching. In other words, we'll walk through having a database of known exploits and then simulate incoming logs being checked against that database of known logs via vector search. And if the distance score, if it's close enough match, based on the distance score, we'll flag it as a possible exploit to be or raise an alert with it, that sort of thing, right? The second area is the opposite of that, which is anomaly detection. So we will walk through building a vector data store of known good logs, benign logs, to use for comparison, and then we'll use those same mixed incoming logs, that some of which are good, some are bad, to check for the worst match against that database of known good logs. And we'll flag ones that are too different as a possible anomaly to be alerted on. And then finally, we'll walk through some examples of semantic clustering. This is clustering done on the meaning of a text passage. And we have tooling to do that, and that's also something that we will leverage, not necessarily vector databases, but vector embeddings to do that. Some vector databases can do clustering, some cannot. In this example, we'll see another way to go about it. So let's dig right into this. The two key components in this, one, of course, is some sort of vector data store that knows how to do hierarchical, navigable, small world, approximate nearest neighbor searches, preferably with large volumes of data. We're not using a very large volume of data. This is running on a laptop, but it would work in much the same way if it were done at bigger scale with different components. So one key piece is a vector database, vector data store. The other key piece of technology that's necessary is an embedding model. And I chose to use Hugging Face Sentence Transformer, one of the mini LM L6 models, because it's a common choice for calculating vector embeddings for general purpose text. So those are the two technologies, and both of those will be running local on this laptop. So neither one is sending any data to any external API or anything like that. It's all within the isolated within the current execution space on a particular piece of hardware in this case. So there's lots of other names vector search is known by. Vector similarity search, semantic similarity search, neural search, AI search, cognitive search, KNN search, approximate nearest neighbor search, ANN, HNSW. There's a long list of names, but they are all referring to essentially the same technology and the application of that particular technology. If you've ever seen the output from a recommendation system, here's a product that other people bought along with the product that you're buying, or here's a song Yeah, you like this song. Here's other songs that are similar to that one that you might also like. There is this AI technology, vector search, behind the scenes is what's driving those recommendation systems. So this is not really, it's new in focus. It's been around and growing for most of a decade, though. So, and it's the vector search part of it is fairly mature at this point. So, where does vector search fit into the big picture? Other types of search that we know about. Relational search. That's relational query. That is essentially SQL statements with aware clause. That is focused on equalities or ranges of data, and it's very deterministic. There's no such thing as a fuzzy match. It's either the condition matches or it doesn't. The next category, in my mind, is full text search, keyword search, right? This is based on finding a word, and it's mostly deterministic, but then it becomes less so, a little more fuzzy when you start to search for the stem word, right? So if you search for driving, you also want to uncover text passages that might have the word drive in them, right? And that's a stem word for driving. Similar examples. And then, the third category is vector semantic search, right? Which is queries done on the meaning of data. And how this works at a high level is you take a passage of text, or it could be an image, an audio file, a video file. You're given an appropriate model. It could be an executable, an actual binary executable. It could be encrypted data, where you don't know what the encrypted data is, but you can still find similarities, right? You can take any of these, given the correct large language model, or given the correct model, and calculate a vector embedding from that data. And if you can calculate a vector embedding, then you can put that into a vector data store and do vector queries against it. So this is the basic idea. So we're gonna walk through these examples that I've told you about. So we're going to load our environment, which is pretty simple. Pandas, ChromaDB. The first thing we're going to focus on, the first step, we're going to focus on the exploit matching example. And step one, the first thing we have to do is build a vector data store of malicious logs. So let's do that. We're going to take this proxy logs malicious CSV file, which I generated from data in this GitHub project. I will post the URL to the GitHub project for this notebook and all of this code, in the description for the video. So we're going to run this. We're going to load this up. We've got IDs, IP address, a timestamp, and the log entry. And essentially, it's a CSV file of that information. We can take a quick look at truncated example. There it is. An ID, IP address, timestamp, and the actual log entry, which is truncated in this particular example, just to make it easier to display. We are going to set up an in-memory instance of ChromaDB, and that will function as our in-memory vector database in this case. There seems to be currently a bug around using persistent storage with ChromaDB. I don't know how long it's been in place or how long that'll be fixed, but it seems to work fine in memory. Also, one minor bug that I seem to have uncovered is, although I'm telling it to use a cosine distance metric, it doesn't appear to be honoring that. It's using its default Euclidean distance metric regardless of what I've told it to do. But we'll still be fine with the example for that. So I'm going to take the IDs, list of IDs, and a list of log entries, and I'm going to hand that to the vector database that's in memory to add. Now this will take a while, So I'll talk through it while this runs. The Chroma, if you hand it text without a vector embedding, then it can automatically calculate the vector embedding for you. It uses one of the Hugging Face Mini LM L6 V2 sentence transformer models to do this calculation of vector embedding. That is a 384 dimension vector embedding that will come back for each proxy log, essentially. And the vector database will then store that ID, the text of the the text that was used to calculate that vector embedding, and then the vector embedding that it came back with. So that is done automatically. Now, alternatively, we could have used any model that we wanted to calculate the vector embeddings ahead of time, and you'll actually see an example of that later in this notebook. It took less time to just hand the whole thing to Chroma and let it do everything in the same process. So that's what we're doing in this particular case. So that finished. It took about a minute. Now, the first time you run this, you will see, if it's not already present, the first time you use this model, actually, you will see the model be downloaded to a known area where ChromaDB can access it, to the local host. So that does reach out to the internet, to Hugging Face's repo, to grab that model and download it, but that is the only external communication that actually happens in this case. We're going to count to just check that we have 1,000 records is what we expect. So we've got a database with 1,000 records that show malicious logs now, okay, with vector embeds. Let's run this and take a look at the first record. So ID1, the numbers that you see is a list. That is the vector embedding. It is 384 numbers that describe the meaning of this piece of text that was in that proxy log. Now, the example that I always point to say, how does this work? What does this mean? Is if you know my location, I'm in Savannah, Georgia, and you could describe my location as a vector, a two-dimensional vector that has latitude and longitude. Now, if you're in New York City, you could describe your location as a vector, a two-dimensional vector, which is latitude and longitude also. In fact, if you know my latitude and longitude in Savannah, Georgia, and we know yours in New York City, you can subtract the latitudes, square it, subtract the longitudes, square that, sum those two numbers together, and then take the square root of them, and that is your Euclidean distance calculation. It's actually a fairly simple calculation. Now, for a vector database, for a vector embedding, for text, we are not looking up the latitude and longitude. We are handing that piece of text to a large language model, and then the large language model is generating or calculating a vector that reflects its understanding of what this text means, and it's handing that vector back to us. So instead of a two-dimensional vector with two numbers, we have a 384-dimension vector, with 384 numbers. And that's kind of how that works. The math that you do with a 384 dimension vector to do those vector searches, it's calculating vector distance. Something that is closer distance, in terms of distance, is a better match. It's just doing, it's the same math that you would do with latitude and longitude with two dimensions. There's just lots more of it, right? So that's really the biggest difference. Now, so we built that database, and let's hand it this URL as a string and tell it to, we're going to do a vector query, and we want the top 3 results back. So what's going to happen is Chroma is going to take this string, it's going to hand that string to that same model, that same sentence transformer model, calculate the vector embedding of this text string, and then it's going to do a vector search against the records that it has to find the 3 best matches. So let's run this. Now, so we've got some matches. Yeah, they appear to be pretty good matches, right? Now, this looks a lot like keyword matching or full text search, but it's actually not. We can add, a actual phrase to search for that is full text, and we'll see, if we look at this, we actually get different results, right? Let's take that out. We can pre-filter we can filter on a particular keyword match and then apply the vector search just to the results that are matching for that. We can also do the same thing if we had given the vector data store any metadata to store, like the timestamp or the IP address maybe would be reasonable metadata to give it. But we ignored those for the purposes of this. So we've got results. Let's do this differently, though. Let's do this a little differently. We've got the distances of the top 3 matches, right? Instead of giving it a URL that looks like, we could just do text matching with it, let's do something that we couldn't do full text search with, and let's ask it a question. Can you show me possible attempts to change a password? Now, we're asking the same question, but we're doing it in natural language. And again, what's going to happen is this phrase will get handed to the language model to calculate the vector embedding, and then the database will take that vector embedding and do a vector search to find the best matches, the top 3 matches. So let's run this, and there we go. We have some matches that look like they're probably pretty good matches. They were trying to touch Etsy password. So those look reasonable. All of them touched Etsy password. All of them failed with a 403. Looks like decent matches, right? Let's take it a step further. Let's do a more general statement. Please show me possible intrusion attempts. Let's see what we get from that. Looks very similar, still trying to touch Etsy password. Now, one of the things that we could do here is say, okay, let's only include things that have the word script in them. So we would apply that filter first, find all the entries that have script, that keyword match, and then do the search just on that subset, right? If we do that, we get matches that seem to be reasonable. So this is good. So we've built a data store of malicious logs, and that appears to be working in the way that we would expect it to work. Now let's do step 2, which is do semantic mashing of those malicious attempts. So we're going to simulate incoming logs. We're going to use our CSV file of proxy logs that are mixed. We have, and since we generated these, we know that there are 950 good logs and there's 50 bad logs. So we're going to use this as our simulated incoming logs, and we can take a quick look at that. It looks the same as that's very similar to the malicious log data, same format, same structure. So I'm going to run this while I talk because it runs for a while. Now we are grabbing the log entry. That's the only part we're really interested in. And for each one of those log entries, we are going to the vector database and doing a vector search that returns we even only need just one result. We are checking the distance value that came back, and if that distance value is small enough, it's equal to or smaller than a certain threshold that we've already preset, then we are going to flag that as enough of a match to the malicious logs that we want to raise an alert. So we've got a database of malicious logs. We've got incoming logs that we don't know whether they're good or bad, and we are doing a vector search with every log, and the ones that are a strong enough match to the bad logs, we are going to flag them and raise an alert. So this just takes a few minutes to run. But it's a good exercise. Again, we are letting Chroma in this case calculate the vector embedding for us, and do then use that in the vector search, and we are getting some examples back. Now, of each pair, the top one is the log that came in, and the second part of each pair is the log that was the best match, right? So if you can look, you can see these do seem to be very good matches. They're similar URLs. They're 500 in 500 error code, so they all failed. Now here's a couple that this one matched, even though this one was a 500 and this was a 400. Yeah, there are some differences like the process ID and some other things, but this is the score. This is the matching score. This is actually the distance metric that's being reported. So there's a decent example. So we have successfully demonstrated creating a database, a knowledge base, a catalog, whatever you'd like to call it, of bad logs, known bad logs, and we are feeding in unknown new logs and doing a vector search with each one and comparing its score, its matching score, and if that matching score is low, or that matching difference distance is low enough, then we are flagging it as a possible alert. So let's move on. In the interest of time, let's move on to the next example, which we're going to do the opposite. We are going to do a form of anomaly detection where we take a database of known good logs, benign logs, and we feed those same incoming logs in, and we do a vector search one at a time with each one of those logs. And this time we're not looking for the best match, we're looking for the worst match. And we'll set the threshold to be, it must be above a certain distance of mismatch for us to flag this as a possible anomaly. So let's walk through that. We are going to use the same vector database just to conserve memory on the laptop. We are going to use our good proxy logs, that generated sample of proxy logs, and we're going to add them. We're going to add those, build that database of benign or good proxy logs to do searches against, and this will take a while. Again, we are handing it the ID list and the text of the proxy log. We are allowing ChromaDB to take the text, calculate the vector embedding for us by handing it to its local copy of the Hugging Face sentence transformer mini LM model. It catches that vector embedding and adds the ID, the text, and the vector embedding that it calculated to its data store, its in-memory data store. So this will take a few minutes to complete. Again, we could have calculated the vector embedding ahead of time with a different model if we had a more accurate model for maybe proxy logs or whatever our domain material is. And then we could have actually just handed Chroma that whole list of ID, the full text that we are using, and it's already pre-calculated vector embedding. We could have done it that way. So that finished. Took about 1 minute and 10 seconds on this laptop. So we've got 1,000 records, which is what we should have. Let's take a quick look at a few. We've already seen the vector embedding. We know what it looks like. Here's the text of good logs. They're seem to be pretty innocuous URLs. They're 200, so they succeeded. It doesn't seem to be anything. I mean, these look like decent examples of good benign logs. So we've got our database built. Now, let's do the anomaly detection exercise, step 2 of this. So we're going to use our mixed logs again that have 950 good logs 50 bad logs. We're going to use those in this example. Here we are, and I'll run this while I talk. So we are taking just the log entry column of the data frame, and we're calling that our incoming proxy logs. And then for each log entry in that, we are handing it to the query operator of the vector data store to calculate its vector embedding, do an HNSW vector search with that. And in this case, we're still only bringing back one result. What we want to find, there are a couple of minor flaws in this, but what we want to find is the worst match. So of those matches that come back, we are looking for a distance measurement that is greater than a predetermined threshold that we've set. In this case, is 0.3. Now, I only know that because I've run through this enough times, so I picked a threshold that would give us a few examples to look at without running some ridiculous amount of time. So, in the interest of keeping the time reasonable, and then we'll output the log that actually triggered the match. And here we go. We're getting some output now. So the first piece here is the incoming log that's triggered, that was being matched to, and the worst match ID based on the score, is a second piece of this. So, and these look like, they look like reasonable results, right? The first one that came in was a 403, and it's definitely quite different from this. The log that it was, a very bad match for, right? This one was an error against the Etsy password, and this one, that it was a non-match to was, a successful hit on example.com. So looks like that's working. So we have now successfully done, taken a known exploit, a database of known exploits, and match incoming logs to that and raised orders with ones that were below a certain threshold of matching, or that were a good match. We have we've built a vector data store of good logs, and then we have taken incoming logs, and we have flagged entries that were not a good match, the worst match, because those might be anomalies. Now let's take a step back and look at how we might do semantic clustering with vector embeddings of full text. And again, this could be vector embeddings of full text, it could be vector embeddings of images, could be vector embeddings of audio files, music, voice, whatever, conversation, speech, books, audio books. Could be vector embeddings of video. Could potentially be vector embeddings of any binary data, even binary executables or encrypted data where you don't know what the content is, but you still want to be able to do similarity matching. So it's might be worth digging into that category a little bit to see how well that actually works. So semantic clustering. We're going for this exercise, and this is the last piece. We are going to use our mixed logs data, 950 good logs, 50 bad logs. We're going to load that. We're not interested in the IP address and timestamp for this exercise. I just, we got the ID, we've got the log entry text. Now, previously, and I'll run this while I talk about it. So, previously we handed this to ChromaDB and let it calculate the vector embeddings for us using the mini-LM L6. And there's no point in handing it to a vector DB to enter and then pulling it all back out. So we're just going to explicitly hand this text to that model and let it give us back the vector embeddings. So you'll see here that's actually pretty simple to do. We specify the model name, standard transformer. We make that our object, and then here just using a lambda function to take the text that gets passed in, which is the log entry, and then running it to the model's encoder function. catching that output, and we're putting that into a new column, a data frame called embedding. So as soon as this finishes, we'll see a sample of a few of them. So it's running. It's again, I'm running this on a laptop. In the real world, you would probably want to run it on more capable hardware like Databricks, Azure, AI search, with some of the models that are private to, or Hugging Face models, open source models, or models that are private to, Azure. To do the same thing with AWS OpenSearch and models that are available within AWS, Databricks. There's a Mosaic vector indexing and vector search feature that was added in January of 2024 this year, and that's called Mosaic Vector Indexing. And they have their DBRX model that's available. There's some ways to also pull in Hugging Face sentence transforms if you wanted to actually go that route. So, but here's our data now. So we started with the ID and the text of the log. Now we got the ID, the text of the log, and we have added a column with vector embedding. So let's go try very basic k-means clustering with 384 dimensions, and we want a k. We know that we have 950 good logs and 50 bad logs. Let's see if we can actually detect that in this clustering exercise. So let's specify a number of clusters as 2. We're going to tell k-means find 2 clusters in this, right? And we're doing this with 384 dimensions, which is a pretty big number. I've tried a few different settings here to see what I could get, but we are going to train this unsupervised k-means clustering model with this data, and then we are going to use it to predict each entry's cluster, and we are going to add a column to the data frame for the cluster number that came out of this k-means. So here we go. This one actually, oops, I accidentally ran the prior cell again. This will take a moment. Let me pause. Let me see if I can pause the recording so we don't have to sit here and suffer through this again. Okay, that finished second time. Now the clustering is actually very quick. So that completed already. We've got our ID log entry embedding column, and we've added a cluster means column. Let's take a quick look at what that looks like now. So we've got the cluster that the model has decided that entry belongs to, and you see it's 100 essentially. So let's look at the unique counts, and what we would hope to see here is something close to 950 and 50 for the 2 groups, but not quite there. 711 and 289. It's not horrible. I'm not sure we're in the same ballpark. We are maybe in the same neighborhood of the parking lot, but we're maybe close to the right ballpark. So let's see if we can work with this and get the numbers that are a little closer to what we actually think they should be. We are going to take a step back and recluster. 384 dimensions is a lot to cluster with for k-means. So we are going to do dimensionality reduction using principal component analysis first, and then we will try to cluster with the k-means algorithm with k equal to 2. So let's do the PCA and build that model, do the transform, do that model. That completes quickly. So now you'll see in the data frame, we still have the log entry, the ID, the embedding. We've got the cluster k-means we computed before. We've got the 2 primary components that we told it to reduce to the dimensions to. So this will try to crunch those 384 dimensions down to the set of 2 most meaningful dimensions that capture the majority of the variance, essentially, is what it comes down to. And we've recorded, or we've noted the cluster, the PCA means, what it found its cluster number for that. Let's check the value counts, the distinct values again. Unfortunately, it didn't change. It didn't get us any closer to the 950. So let's try something different. First we can actually visualize, since we have it in 2 dimensions now from the PCA, the principal component analysis. We can actually graph this. Take a look at what it looks like, what the reduced dimensions look like when they're plotted. So we can see that there do appear to be 2 distinct groups of data. This that's on the right side, smaller group on the right side, and this on the left. This is obviously the 289, and this is the 711. Let's keep going. So k-means uses Euclidean distance for its clustering. We know that for text, cosine similarity actually tends to give better results. So k-means doesn't directly support cosine similarity, but we can take the vector embeddings and rescale them such that when you do the Euclidean distance calculation, what you're actually getting is cosine distance. So let's do that. We're going to do that exercise, and we've added a column called cluster means cosine to our data frame from that, which is the cluster group that row is assigned to. Let's check our value counts, distinct value counts. We've still got 711 members in group 1 and 289 in 0. So maybe the data is not linear. Let's try some nonlinear algorithms for clustering. Let's try agglomerative clustering, which is a hierarchical algorithm that's nonlinear. So we're going to work through that. And let's see, we're using the metric of cosine. So we're using cosine distance for this. So that's pretty quick. Let's see what our value counts look like. So we've got a model that's agglomerative clustering model, and we've used it to predict the membership, the column, and we've added that to the cluster underscore agglomerative. We've added that column to the data frame. So we're going to look at the value counts there. Unfortunately, they're still the same, 711 and 289. So let's graph this in a different way. If we're assuming that maybe it's not linear data, then let's use a nonlinear dimensionality reduction algorithm, t-SNE, instead of PCA, which is linear. So let's try that and plot it in 2 dimensions, and let's see what it looks like. So this is a little more meaningful. We are seeing some differences here, but it's still not telling us a whole lot about the content of the data. So let's take a step back. We need a clustering algorithm where instead of us telling it the number of clusters that we want to see, let's try a clustering algorithm that will actually go discover the most likely number of clusters for us and report back on what those cluster groups are for each row. So let's use that instead. This would be dbScan clustering. It's nonlinear. It's density-based clustering, and we're going to use cosine distance as our distance metric with that. So let's run that. And as I had mentioned, it will figure out the number of clusters. It found 8 clusters. And we've added a cluster dbScan column to the data frame to tell us which cluster that row is from. Let's look at the value counts. Now, my eyes immediately go to the 289 because we've seen that so many times. So that is a group, that 289, whatever it is, that is a group that the dbScan clustering found that are similar. And we don't know what the similarity is, but we know they're similar. Now, my eyes also immediately go to group number 2, which has 53 members. That is very close to our 50. We know that we have 50 bad logs, and 53 is an awfully close number. Let's apply PCA to the clustering, or the clustering, the groups, and so that we get it down to two dimensions that we can plot. And let's just plot the PCA, the principal component analysis output of this clustering exercise with dbScan. So now we are gaining some visibility into this. Here's that 289 that we've been seeing in the other clustering algorithms, but now we're seeing this group also has some differences that are being found by the dbScan. And here I'm pretty sure I'll bet this is the 53 group of 53 members, and I'll bet that's our bad logs right there. It could be this, it could be maybe the yellow, but I would suspect it is this. So this, I think, this was a very meaningful exercise to let dbScan, which will also work with very large volumes of data, go through and find the numbers of clusters for us. So I think this was actually this last step was very revealing. So we suspect our bad logs of this lighter green group, right? And that's good to know. Now, we've got the data frame with all this. We could go just dig into the data and look at it and do further analysis on those subsets, right? There's no reason that we couldn't do that. But this is actually fabricated data. This is fake data. There's not really a whole lot of value in doing that. If you are using your data, your security logs, your customer reviews, any sort of text data that is your production data for this exercise, then it's definitely worth digging into those different segments to figure out what's causing this grouping. How are we getting this grouping, right? So there you go. That's all I have to show you. The URL to the GitHub account with this will be on your somewhere in the video description where you'll be able to get to it and pull this code. You can also go to github.com, David C. Sisk, my name, and you'll see a variety of repos, and one of them will be the vector search with security logs. So thank you for your attention. I tried to keep this as short as I could. I know it's still fairly long. It's a lot of info, but I think it's actually very interesting stuff. The amazing take home for this is that we were able to do matching with full text. We were able to do anomaly detection with full text. We were able to do clustering with full text. We talk about all this data that we're creating on our planet, and some very large percentage of that is all full text data. So we need tools, techniques, and processes that work reliably and are manageable in terms of volume for this, this huge explosion of full text data that we have to deal with in business and government and public sectors and private business and research areas. So anyway, thank you for your attention today, and I hope you thoroughly enjoyed this. And feel free to ping me with questions if you'd like. Thank you.